Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So students, today we are going to discuss about the module Masses of Stars from the paper Astronomy and Astrophysics. So after studying the module, you will be able to understand that the mass of a star is an important property because it determines the rate at which it evolves. Appreciate that the mass of a star can be estimated directly only when it is in binary group so that the laws of Kepler can be applied. Luckily, most stars are found in binary groups. Recognize that binary stars could be visual binaries, spectroscopic binaries, or eclipsing binaries. These names are quite descriptive. Visual binaries can be resolved directly by an optical telescope and their orbit can be charted. Next, you will be able to understand that the spectroscopic binaries are recognized by the oscillating set of lines in their spectra. Oscillations can be converted into light curves which can be analyzed to give the orbital elements of the system. Lastly, you will be able to appreciate that the inclination of the binary orbit to the plane of the sky is usually not known, in the absence of which we can apply or we can only find out the lower limit of the combined mass of the system. So students, let us start with a basic introduction about the module. So far, we have dealt with the properties of stars like their surface temperature, luminosity, and nature of spectra. Based on their spectral properties, stars have been classified in 7 major classes. A chance observation of correlation of luminosity with the surface temperature of stars led to the development of HR diagram and luminosity classification of stars. HR diagram and its variant color magnitude diagrams have been of immense use to astronomers and astrophysicists in learning about the evolution of stars. Several times it has been said in these modules that the mass of a star is an important parameter in determining the rate at which it evolves. It is therefore the time that we learnt how the masses of stars are actually determined. The next few modules are devoted to this topic, and we shall find that not all star masses can be determined directly. So these stars whose masses can be found directly are used to establish the relationship between mass and luminosity, called as the mass-luminosity relation. Masses of most stars are then found indirectly using this relation. Binary stars. A major source of information about the stellar masses is the group of stars. Binary groups and groups of 3 or more stars are the accidents of birth. So the processes of stellar birth seems to favor the formation of stars in the groups rather than single stars. So in a group, the stars are held together by the force of gravitation, and it is the application of Kepler's law based on Newton's law of gravitation that allows us to estimate the masses of their components. A large majority of these stellar groups are binary groups, as shown in this figure, which shows that the center of mass is, that is Cm, of the binary system in which M1 is greater than M2, and here the Cm is nearer the more massive star. So the center of mass of a binary system is such that M1A1 equal to M2A2. It is also necessary to recall from classical mechanics that if one star is made the origin of the system, the motion of the system is reduced to that of one star executing an elliptic orbit. In about 5% of these groups, the stars are attended by a third components. So now students, binary groups shows a large variety of groups, and in some groups the components are so far apart and they are bound so loosely that even a weak disturbance can drive them asunder. On the other hand, in some systems, the components are so close that they are almost in contact. In the latter situation, two stars that are exerting tidal forces on each other become elongated along the line joining them. So these close binaries exchange masses between them, and in some cases the interaction between the stars lead to a net loss of matter from the binary system. So these are the figures showing the two examples of a binary group. The left hand side figure shows the WZ C5 binary group, and the right hand side shows the Eta Carinae group consisting of Eta Carinae A and Eta Carinae B stars. This shows a fraction of binary systems have a third component also, and the example is given over here, containing 3 stars, Alpha Centauri, Beta Centauri and Proxima Centauri. So depending on the way in which a binary group reveals itself, it may be a visual binary, a spectroscopic binary, or an eclipsing binary group. In a few cases, a binary group may be visual as well as eclipsing, or it may be a spectroscopic as well as eclipsing. Such groups are more useful to us as they give information not only about the masses of their members but also about their sizes. Visual binary stars. A group of stars which can be identified as a binary with unaided eye or with the help of telescope is called as a visual binary group. According to the law of classical mechanics, both the stars must execute elliptic orbits around the center of mass of the system. However, if one component is much more massive than the other, then this more massive component makes a small ellipse about the center of the mass, and the less massive component goes around in a larger elliptic orbit. The more massive component is called as the primary, and the less massive component is called as the companion. The plane of the orbit of the group is in general is inclined to the plane of the sky, defined as the plane perpendicular to the line of sight. So when projected on the plane of the sky, the elliptic orbits remains elliptic, but the primary may not be at the focus of the ellipse as shown in this figure. In actual fact, the center of mass, also called as the barycenter of the system, may not be at rest. So in that event, the two components of the binary group will trace out serpentine paths in the sky, the center of mass of the system always moving in a straight line. Because to a very good approximation, there is no net external forces acting on the system. The paths may be further complicated by the presence of the third component and the parallactic displacement of stars. It is from these complicated paths that the elliptic orbits have to be retrieved. The orbits on the plane of the sky is called as the apparent orbit. So the epoch corresponding to each position of companion on the orbit or of both the components, if the orbits of both are visible, is carefully noted. An analysis of the apparent orbit can furnish the period P, eccentricity E, the separation of the two components A, and the inclination I of the sky of the true orbit to the plane of the sky. Stars are surrounded by other stars from all the sides. So the vector sum of all gravitational forces acting on any star is therefore 0. Thus, there is no force on the center of mass of a binary group. The center of mass Cm moves in the sky in a straight line. So the two stars of the group move around the Cm, executing serpentine motions in the sky. So this is the motion of the group that is actually observed. So this figure shows that the center of mass of a binary system, also called as barycenter, is in a motion along a straight line because there is no net force acting on the system. And here the two stars oscillates about this center of mass. So this is the motion of the group that is actually observed, and from this complicated motion is derived the binary orbit of the group. Spectroscopic binary systems. So now a category of binary systems cannot be resolved visually. Their binary nature is revealed through the oscillations of their spectral lines. So consider this figure. When the two components are moving across the line of sight, their spectral lines overlap and we see only one set of lines. When the two components move along the line of sight to Earth, the lines of one are Doppler shifted towards red, while the lines of the other shift towards blue. Thus we see two set of lines. So, as the stars revolve around their common center of mass, the spectral lines oscillate. So, if one of the components of the system is too faint for its lines to be seen, we see only one set of oscillating spectral lines. The displacement of a spectral line from its unshifted position can be converted into the radial velocity of the star with the help of the Doppler formula. That is, after taking due care of the motion of the Earth. So, and plotted against the phase phi equal to 2 pi by p to get what is known as the velocity curve. If two sets of oscillating spectral lines we get, then one can get the velocity curves for both the components of the binary system. A careful analysis of the velocity curve yields information about the elements of the orbit from which the masses of the binary components may be gleaned. After the elapse of another quarter period, the direction of shift caused by the motion of stars is reversed. The lines which were earlier shifting to red now shifts to blue, and the lines which were earlier shifting to blue now shifts to red. Another quarter of a period later, stars are again moving across the line of sight. So there is no shift and the lines are seen in their original position. After another quarter period, the cycle has been completed. Thus, as the two stars move in their orbit around the center of mass, we see set of oscillating lines. If both the stars are bright, we see two sets of oscillating lines. If only one star is bright enough for its lines to be seen, we see a single set of oscillating lines. By measuring the shift of the oscillating lines to the red and the blue radial velocity curve is obtained. So as students, you can see over here that at point B and A, the companion is moving across the line of sight. So radial velocity at this phase of the cycle is 0. Now at point C, the companion is pedestrian and it has a higher velocity and therefore a larger shift that at a point D, when the companion is near the apastron and its velocity is lower. Orbital elements of a binary system. So students, suppose PMQL is the actual orbit of the star as shown in figure A. Let NOL be the line of nodes, that is, the line of intersection of the plane of the orbit and the plane tangential to the celestial sphere. Let PQ be the line of apsis, the line joining the periastron and the apastron. If phi be the position angle of the star at any moment measured from perihelion, and omega be the angle between the line of nodes and the line of axis, then y is equal to r sine of phi plus omega. So, where r is the radius vector of the star, since the actual orbit is inclined at an angle I to the plane of the sky as shown in the figure B, the displacement along the line of sight is given by z is equal to y sine I equal to r sine of phi plus omega multiplied by sine I. So in this figure B, as you can see over here, that is, there is the elements of the orbit of a binary star, and the plane of the orbit is pi, while t is the plane of the sky, and the angle between the two is I. Velocity curve. If we assume the center of mass of the binary system to be at rest, then the radial velocity is given by Vr equal to dz by dt, where Vr equal to sine of phi plus omega sine I dr by dt plus cos of phi plus omega sine I multiplied by r d phi by dt. So the two derivatives dr by dt and r d phi by dt are found with the help of the equation of the elliptic orbit, that is r equal to a multiplied by 1 minus e square divided by 1 plus e cos phi, and the equation for the Kepler's law of equal areas, that is d phi by dt equal to 2 pi a square by p r square multiplied by root of 1 minus e square. So, putting the value in the equation for r, we get, that is, if we take the derivative of r with respect to t, then dr by dt equal to 2 pi by a p multiplied by root of 1 minus e square multiplied by e sine phi, and then r d phi by dt can be obtained by multiplying the expression of r with the expression of d phi by dt. Now, putting the values of dr by dt and the product r d phi by dt in the equation of Vr, we get Vr equal to 2 pi sine I by p multiplied by root of 1 minus e square multiplied by cos of phi plus omega plus e cos omega. So it is possible that the center of mass of the system may be moving with respect to the sun, and even in unshifted position, the spectral lines may be Doppler shifted. Let V0 be the radial velocity of the system with respect to the sun, and then Vc denotes the total radial velocity of the companion, then Vc equal to V0 plus Vr. It is obvious that the integral of Vc over one period of the system must vanish. This means that the value of V naught is such that the velocity curve occupies equal areas above and below the line Vr equal to V naught. So now for the observer, the maximum and the minimum radial velocities occurs when the position of the star is on the line of nodes, that is, it is given by Vr max equal to k multiplied by 1 plus e cos omega, Vr min equal to k multiplied by minus 1 plus e cos omega, where a constant k equal to 2 pi a sin I divided by p multiplied by root of 1 minus e square. And k can also be expressed as Vr max minus Vr min divided by 2. Now the equation k e cos omega equal to Vr max plus Vr min by 2, and this is represented as Vr med, that is the median radial velocity. So now students, we can write the radial velocities at periastron at phi equal to 0 and apastron at phi equal to pi as Vr peri equal to Vr median plus k cos omega and Vr apastron equal to Vr median minus k cos omega. So now if we know the instants when the star is at periastron and apastron, then this equation determines k cos omega. So from these equations we can calculate k, e, omega and a sin I, and p being the velocity curve. So the instant t peri is found by plotting the quantity Vr as a function of t plus Vr as a function of t plus p by 2 as a function of time, and looking for the instant when the function assumes a value 2 Vr median. Because in the view of equations, this equation that is Vr peri and equation Vr apastron, we can write Vr as a function of t peri plus Vr as a function of t peri plus p by 2 equal to 2 Vr median, so that the instant t peri is easily determined from the velocity curve. Masses of stars of a spectroscopic binary system. It is possible to combine these two equations to get m1 plus m2 multiplied by sin I to the power cube equal to p by 2 pi g multiplied by k cube multiplied by 1 minus e square to the power 3 by 2. It is usually to express the velocity in kilometers per second. So the period p in days and the stellar masses in the units of solar mass. Then m1 plus m2 sin I to the power 3 equal to 1.026 multiplied by 10 to the power minus 7 p multiplied by k to the power 3 multiplied by 1 minus e square to the power 3 by 2. So let us write m1 plus m2 equal to 1.026 multiplied by 10 to the power minus 7 pk cube multiplied by 1 minus e square to the power 3 by 2 divided by sin I to the power 3. Since I can be determined only if the spectroscopic binary system is also a visual or an eclipsing binary system. In the absence of such a coincidence, I is not known. So the numerator on the right side of this equation gives then the lower limit of the combined mass of the system. So if one star of the group is much more massive than the other, then the Cm may be within the massive star as shown in this figure, that is, which shows the Sun-Earth system. As the less massive star orbits around the Cm, the more massive stars appears to wobble from side to side. So the observed wobbling motion is indicative of the star being accompanied by one or more planets. The Cm, or the barycenter of the solar system, wobbles in space as observed by observers outside the solar system. The wobble is dominated by Jupiter and some extent by Saturn if their masses are set to zero. The simulations shows that, and they are shown in this figure, the wobble motion of the Sun becomes very weak. So students, let us summarize what we have learned in this module. Mass of a star is an important parameter which determines the rate at which it evolves. Most stars exist in binary groups and groups of 3 or more stars. Applications of Kepler's law to the binary groups is the source of stellar masses. Binary groups can be visual, spectroscopic, or eclipsing binary groups. Visual binaries are accessible to observation with telescopes. Spectroscopic binaries, they reveal themselves through an oscillating set of spectral lines. Eclipsing binaries are recognized when one component eclipses the other and gets eclipsed in turn. The more massive component of the group is called as the primary, while the less massive is called as the companion. Since the center of mass, or barycenter of the binary system, moves in a straight line in the sky, the two components move around this, moving the center, and execute the serpentine motions in the sky. So the orbit of a binary system is an ellipse. The plane of the ellipse is generally inclined to the plane of the sky. The orbit projected to the plane of the sky is also an ellipse, but the primary is not at the focus. Kepler's third law can be applied directly to the visible system. If both the components are visible, mass of individual member of the group can be found. By studying the behavior of oscillating lines of the spectroscopic binary system, we can plot the velocity curve of the binary system. Analysis of velocity curves lead to the determination of orbital elements of the system, which leads to the determination of stellar masses. Since the inclination of the orbit to the plane of the sky is not generally known, we can place only a lower limit on the combined mass of the two stars. The masses of only a small fraction of stars can be found by analyzing the binary systems. These masses can, however, be used to establish a mass-luminosity relation, which can be used for finding masses of most stars. Thank you.